Welcome everyone. In this video, we will solve a numerical which is based on the bandwidth extension in negative feedback. So H, the title is there, bandwidth extension in negative feedback. So this is a question from the feedback, okay, feedback circuitry. So in this question, a non-inverting op amp is given. So here this one is the non-inverting op amp. So it is given, let the open loop gain A have low frequency value of 10 to the power 4. So basically the gain of the amplifier is given as 10 to the power 4 and the corresponding minus 6 dB per octave roll off at high frequency with a minus 3 dB frequency is given 100 Hz. Okay, so then we have to find the low frequency gain and the upper 3 dB frequency of a closed loop amplifier. Okay, so basically, so this one is a question from the feedback. So first I want to give you a brief of some theory behind it. So basically I am plotting the gain in dB and frequency also in log scale. Okay, log scale. So when there is no feedback, so the amplifier gain with frequency curve is somehow, okay, this one is the curve. Okay, it should be uniform. So now I am saying this one is the am amplifier constant gain. Okay, so for the time being, now I am just showing you, just consider this as a amplifier section. This one is our amplifier section, and below that one, this one, okay, below that one, this one is a feedback one. Okay, so I am just writing this one is the feedback amplifier, we can say, and this one is our basic amplifier. Okay, so for the time being I am saying this one is a amplifier gain. Say am is the gain, open loop gain. Okay, is am. So the given thing in our question is given is am is 10 to the power 4. Okay, for more detail I will give you the theory behind this bandwidth extension which I have already made. I will put that theory link in your description box so you can follow that theory. Okay, it is also easy, so you can check it out from our description box. Okay, so am is 10 to the power 4, so it is already given, and a uniform minus 6 dB per octave, that is our this one, minus 6 dB per octave, or better to, also we can write minus 20 dB per decade. A first order slope is given. Okay, and this value is given, that is our, we can say, f h. Okay, and a uniform minus 6 dB per octave roll off at high frequency is given, that is our fh. So in this question, fh is given for the particular amplifier is 100 hertz. Okay, and the r1 value is given 1 kilo ohm. Okay, and the R2 value is given 9 kilo ohm. Okay, so now this one is a problem of a negative feedback. So in negative feedback, as we know, there will be bandwidth extension. So if there is a feedback, so after feedback the bandwidth is increased. Okay, so I am like making like that, and this particular point we can say, and for the time being now I am saying this point is a FL. So after feedback, this point is nothing but simply our FLF, and this point is our FHF. The whole theory I will give in my description box. Okay, link of that particular theory. So this one, so after feedback, this one is decreased by AM by 1 plus AM beta. Okay, the gain will be reduced in negative feedback as we know, and the FHF, the higher cutoff frequency, HFF will be increased by the the open loop frequency plus 1 plus AM beta. Okay, and the low frequency FHF, the FHF value, sorry, now we have to say FLF, FLF with feedback is nothing but simply FL, and it will decreased. So we have to just divide with 1 plus AM beta. Okay, this one is decreased, that's why it coming towards the y-axis. This is going away. Okay, so this one is the theory, and the corresponding gain with feedback, that is our AM F will be AM by 1 plus AM beta. Okay, so this one, the formula is very important. So more detail, you can follow my video on this topic. I will put the theory link in my description box. So this one is the three important thing that we have to know, and this one is the concept of bandwidth extension, we can say. This one, so I am also writing this one is the extended bandwidth. So we can write as bandwidth extension in negative feedback. Okay, so this one, initially the bandwidth is this one, now the bandwidth is increased in negative feedback. So we have to find out the value of, find the low frequency gain. Low frequency gain, that is our AMF, we have to find out. Okay, and we have to find the upper 3 dB frequency of a closed loop amplifier. After putting this feedback, we have to find out the 3 dB frequency, upper 3 dB frequency. It is our FHF. We have to find these two things, we have to find. Okay, these two we have to find. So in AM is given, but beta is not given. So beta is nothing but simply our feedback amplifier gain. Beta is our V naught, sorry, better to write VF, the output feedback, that is our this feedback plus or minus VF by V naught. Is it? VF as a output V naught, and this one is our, say this one is one resistance is there, R1, R2 is there, and we are saying this one is V naught, and we have to find out this VF. Okay, so this one is just voltage division rule. So if you apply simple voltage division rule, we can simply write VF equals to V naught into the corresponding resistance R1 divided by R1 plus R2. So one can write VF by V naught, which is our beta, feedback amplifier gain. Beta is R1 by R1 plus R2. So R1 value is 1 kilo. So I am writing 1 kilo. So 1 plus 9. Okay. 1 plus 9 kilo ohm. Kilo should be cancelled. So it should be 1 by 10 or it is our 0.1. So we can write beta value is our 0.1. Okay. So this one is the important result. Okay. Now beta is known to us. So we can easily find the other parameter that we are looking for. Okay. So the value of AMF, feedback amplifier gain, okay, is reduced by a factor, that is our amount of feedback, AM beta. So AM value is given 10 to power 4, so better to write 10 to power 4. 1 plus 10 to power 4 into 0.1. So it should be our 10 to power 4 by 1 plus 10 to power 3, or if we solve this one, it should be 1001, and if we solve, we can easily find the value of AMF, and if we have to calculate, its value will become 9.99. So the AMF value will be 9.99 unitless. Okay, so this one is one value, that is our AMF. Okay, initially it is 10 to the 4, but now it is 9.99. Okay, now we have to find the value of FHF. So, okay, so I am taking some different color. FHF. Okay, so it should be our bandwidth will be increased. So FH times amount of feedback, 1 plus AM beta. So FH value will be, is given 100 hertz. Better to write 100, and 1 plus AM beta, that is our 1 plus, I am writing 10 to the 4 into 0.1. So it is 100 into just 1000. Oh, sorry, 1001. This one is the value. So if we have to write in kilo, so better to multiply with 10 and divide with 10. So one can write 1001 by 10 into 10 to the power 3. We can write this and this as a 10 to the power 3. So it is just 100.1 kilo hertz. So the FHF value will be 100.1 kilo hertz. So this is all about this question. Okay, but you have to know the theory. Okay, so the theory is this one, is important theory, and it is a negative feedback one question. So, and it is taken from the Microelectronics book, Sedai and Smith, the author of that book. So you can find this kind of numerical in that book, and I will give the theory of this particular bandwidth extension in the description book. So this is all about this question. You have to apply the simple concept. In negative feedback, the FHF value will be increased by the amount of feedback into the original frequency of the, that is our FH. Okay, and FLF will be decreased by the amount of feedback. Okay, so this is all about the theory and the corresponding numerical. Okay, so thank you for watching this video. Thank you.